Okay, the last speaker is Paul Konstantin Ullmann from Uppsala University, and he's going to talk about sections, my section, and the mirror simulating theory. Please start.
Great. Yeah, thank you very much. Of course, let me start everyone and the organizers of the Yarrow Center for giving me the chance to speak about my work and to show my research program. And I hope everyone is not too exhausted. I'm the last speaker for today, so I hope I can do a good job. And so the work that I'm going to present is something that I've started to work on like already roughly 6 years ago in 2014, starting with these publication. And I've continuously working on this topic, which incorporates sections, multi-sections, and mirror symmetry in F-theory with various collaborators. So all these collaborators I have worked with in various constellations. And we have touched upon this topic and produced these papers here. A couple of them are still in progress. And but I will of course not talk about all of them, but these are all the publications that will touch on this topic in one or the other way. Great. So let me first start by motivating. So for me, string theory is something like a dictionary. It's really something that that is something like almost like a Rosetta Stone that is able to communicate problems that we have in physics on the one side to mathematics or geometry. And this is of course great because I have now the possibility to encode things or problems on the one hand in terms of the other. And this is of course an incredibly interesting and enriching point of view, as I'm now able to make progress on one side by using basically the formulation in the other. So one great example itself was the observation of mirror symmetry. So if I compactify the heterotic string on a Calabi-Yau threefold and use the standard embedding, I will find in my lower energy effective theory a gauge group of E6 and a bunch of 27s and 27 bars. But from the geometric computation, those 27s and 27 bars, they come from the Hodge numbers of the underlying geometry. But E6 now has an outer automorphism that interchanges the 27s and 27 bars, and physics of doing so, so just interchanging what I mean by 27 and 27 bar is equivalent. But on the geometry side, you're doing something very drastically because you're changing your interpretation of what volume moduli and shape moduli of the underlying geometry are. And this, of course, has led to lots of progress on the math side in terms of mirror symmetry. But of course, also math or geometry can teach us a lot for physics. So for example, if I just take type 2B strings and I compactify that on some local space, which is something like a local orbifold, what I can describe by this is a very, very exotic and interesting theory in physics, namely so-called 6-dimensional superconformal field theories. And actually, the mere existence of such theories was longly not clear because it's highly long. It's not Lagrangian at all, and it has tensionless strings in the spectrum. And it is really these geometric arguments that that made progress possible on that side. So the specific dictionary that I want to talk about today is not the standard or not the specific string theory dictionary, but the one of F theory. So F theory actually takes all this idea by itself pretty far by being able to describe type 2B string compactifications with varying coupling constant in giving to an n equals 1 dimensional theory and d equals 12 minus 2n. By describing this configuration via a torus fibered Calabi-Yau n-fold. And there's a lot of nice connections and topics that you're having here on the physics side. For example, I can now start to ask questions. What is actually the landscape of all these compactifications, and what constraints do I get for supergravity theories? And this, of course, supports the so-called swampland program. But I can also, like I just said, naturally construct superconformal field theories. I can ask to couple the two together. I can construct 60 SCFTs and connected to this supergravity question, I can ask what kind of phenomenology can I get out of this? Can I construct the MSSM or GATS? On the math side, on the other hand, of course, I can make progress by formulating this in a physics way by asking what is the landscape of, say, elliptic Calabi or n-folds, and what are the enumerative invariants of those? And I can ask things about questions and structures like the so-called model Weil group and genus 1 fibrations, and or even very exotic phenomena like the so-called multiple fiber phenomenon and non-flat fibrations that will all in some non-trivial way connect to physics on this side. So these are all topics I've worked on. And for this talk, I can only select a certain subset of those. And yeah, I hope I can, I hope you find them interesting, I guess. Good. So I start with a quick review in order to get everyone on the same page of what F-theory actually is. So actually F-theory means that you take the type 2B axiodilaton and complexify that, and you interpret the structure as the complex structure of some auxiliary torus that sits over your physical base space. And this is motivated by the observation that type 2B has precisely an SL2Z self-duality, which you can identify with the geometric action of this underlying torus structure. So putting a D7 brane in your geometry is then something like a defect that acts non-trivially on this axiodilaton. So if I circle around this D7 brane, it shifts my axiodilaton and back reacts on it, so to speak. And if I go precisely on the locus of such a D7 brane, the torus will actually degenerate. The consistency of this whole construction is actually given also by duality to M theory, such that this whole geometry is actually a Calabi or n-fold, and it must be, of course, torus fibered. Great. So the first question you ask when you're a physicist, great, this is a nice construction. Which gauge groups can I actually engineer? And here, this is the first time where math actually helps a lot. And so first you have to write down what is actually description of a torus. And there's a nice algebraic description, which is the so-called Weierstrass form. It's given here, which parameterizes this complex structure in some redundant manner via these functions f and g. And I can actually write down the so-called discriminant, which is this combination of f and g. And when this discriminant becomes singular, which happens at specific loci in my base, where exactly the D7 branes are localized, it vanishes. So this is, when this guy here vanishes, it tells you that your torus becomes singular. And we have just identified that with the loci of D7 branes. The nice thing there is that Kodaira classified how F, G, and delta can vanish, and what the monodromies of those are, and what, in physics terms, the underlying gauge groups of those are. So this is, again, a very nice success between math and how it helps physics, because there is a classification of singularities of this torus, which gives us, as physicists, a dictionary to which gauge group it corresponds. And the exciting and the super nice thing about this is, of course, that this is a one-to-one correspondence. So all these singularities are in one-to-one correspondence to some ADE group, which is super nice for physicists, of course. So I'm able to construct all kinds of ADE groups in physics. So, but there's a couple of other gauge groups possible, in particular, like abelian groups. So what encodes those? And there has been lots of progress in the last couple of years. And they actually arise when your elliptic fibration admits more than one section. So what is a section? A section is essentially a unique point on your torus fiber, and you need that when you have your full fibration in order to identify the base. because it's a point on the torus, and at the vanishing locus of that guy, you will identify the base in your fibration. And you can now engineer something like this slightly different Weierstrass model that you're having here, this constrained Tate model, that has more than one section. So one section is really a point on the torus. You have here the x, y, and z, the torus coordinates that are given this vanishing locus. This is the so-called zero section, but you can also have more than one section, which you're having at this locus here. So then you basically have a second section, and actually having the second section on the torus induces an addition law. And this is a so-called model while group law that I'm having. So I'm able to add sections together and get another section. And this is like a highly abstract concept and very non-trivial. And this model while group can actually be decomposed into a free part and a finite part. And it turns out that this free part leads to a billion gauge groups in the F-theory dictionary. And the finite part leads to gauging of a center of some covering gauge group. So these will lead to non-simply connected gauge groups. Great. But then there's, of course, more. What about discrete gauge symmetries? Discrete gauge symmetries are present when there's no section at all. And in order to describe those, you actually have to change the fiber type. You cannot just use a Weierstrass model, since a Weierstrass model always has a section, but you can, for example, describe your torus as a quartic in P112, in this different kind of ambient space. And it's given by this quartic polynomial here. And this guy does not have any section, but it only has a 2 section. Turns out that this gives rise to a Z2 gauge symmetry. And the argument you can have for this is by actually doing some kind of conifold transition, by getting rid of some of these, by basically getting rid of this 2 section, by tuning away some of these coefficients here. So if you set here x to 0, you will find that you have to solve a quadratic polynomial in these a's here. And by the way, I should say the a's are the analogous expression to f and g in the Weierstrass form. So these are certain polynomials that depend on the base. And if I want to solve this quadratic polynomial here in z, I will have certain branch cuts that relate the two solutions of the multisection. But if I'm able to tune some of them away, for example, switching off A4, I will just have linear expression in Z, and actually my 2 section X will split up into 1 sections, and I will get a model Weyl group. So what I've just done in physics terms, I have unhixed the discrete gauge symmetry into a U1. Great. And there's of course more intricate structures here, namely these N section, these genus 1 fibrations that do not have a section. They are part of a more larger group, which is very abstract, the so-called Tate-Schaffer-Ravitch group, which is essentially the group of all Calabi-Yau, torus fiber Calabi-Yaus with the same base and the same Jacobian. Okay, so this is a very abstract group, and is believed that a subgroup of this one has to encode the discrete symmetry that we observe in the physics terms of F-theory. So already the thing that I'm observing here gives you something like a nice conjecture for geometry and physics, which is exciting because there's a so-called quantum gravity law that tells you that I should always be able to unhix a discrete gauge group into an abelian gauge group due to black hole arguments. So I should always be able to take Zn and unhix it to a U1. And U1s are encoded by the model Weyl group, and discrete groups are encoded by this Tate-Schaffer-Ravitch group. So the quantum gravity law then suggests for math, for example, that there should always be some kind of conifold transition that makes Tate-Schaffer-Ravitch or links Tate-Schaffer-Ravitch to some different geometry with a non-trivial model Weyl group. So this is just an example how math and physics can help each other via these various conjectures. Great. So ADE groups are clear, but the things that I just told you about, they are unfortunately not so clear. So these abelian groups, they don't have a nice classification like the one that Kodaira provided us. And but what we know, of course, is due to Mark Gross, we know that, for example, the space of all elliptic Calabi-Yau threefolds, or also K3s, is finite. So if you ask for a similar classification here, and we would, for example, ask, what is the maximal amount of U1 symmetries? What is the highest discrete symmetry I can have? How much of a center symmetry can I gauge in this geometric terms? We just know that there's a bound because there's a bound on elliptic threefolds, but we don't know what the actual bound is. And I should, of course, say that in recent years, there was some improvement on the maximal bound using actually quantum gravity considerations by Lee and Weigert. But the goal of this talk is to somehow improve on these lower bounds here, which is interesting for physics and also interesting for math, of course. Great. So this is essentially the outline. First of all, I will give some physics applications in order to remind ourselves why these structures are actually important for physics. Then I will tell you how I'm planning to put bounds on this model-wide torsion group from modular curves. And then I will further link these structures via mirror symmetry on the fiber and mirror symmetries on the full Calabi-Yaus. Great. So why do we care as physicists? And so I'm actually very thankful to the speaker before because he gave the perfect motivation. Because we do care, first of all, abelian symmetries are part of the MSSM. So if I want to construct the MSSM using F theory, I have to know something on how to construct abelian gauge symmetries. And similarly, if I want to construct something like the Patti-Salam model, it only has this SU4, SU2, SU2 gauge algebra structure, but the global structure is more non-trivial and it has this modding structure here. And in fact, the same is also true for the trinification model, which I have not put here. And using our knowledge about these abelian group structures, we were actually able to construct those groups directly in F theory a couple of years ago, including really a full Calabi-Yau fourfold and the fluxes and so on with 3 generations. So this is one motivation, model building. Another motivation that I want to focus a little bit more is the construction of 6-dimensional SCFTs with non-simply connected gauge or non-simply connected symmetries by using model Weyl torsion. So let me review the structure really quick. So in order to engineer such a 6-dimensional SCFT, what you have to consider is a base, so a complex 2-dimensional base, which is of that shape here. So first of all, it is non-compact. This is something you need in order to decouple gravity, what you want in order to get an SCFT. But then it has a structure of this intersecting spheres here that are compact P1s, complex projective spaces, with a self-intersection number n, and they can carry some kind of gauge symmetry. And the box on the outside is something like a flavor symmetry, yeah. Some which you can maybe get from some non-dynamical brane. So in type 2B strings in F theory, you now have the 3 branes that can wrap these P1s here, and they give rise to massive strings. And the massive strings have a string tension, and well, which is essentially their mass, which is precisely given by the volume of these P1s. So in order to get these massive strings massless, which will then support me as 60 SCFT, I will have to shrink this whole configuration here, apart from the flavor branes, of course. So if I'm able to shrink this all down to a point, all these strings become massless, and I will get an 60 SCFT due to the massless strings. Great. So this is the basic cooking recipe, and what I can now start with is engineering these SCFTs. And the simplest building block for those are the so-called superconformal matter theories. And yet the simplest of those is the so-called E-string theory. And you get it by essentially colliding an E8 singularity with an SU1 flavor brane. And the Weierstrass model will tell you that you will actually get non-minimal singularity. And in order to get rid of this, you resolve this collision, and you get this -1 curve here. So the important point is here that a -1 curve has no gauge symmetry, but it has an E8 flavor symmetry. So this is when I don't have torsion. But if I switch on model while torsion, and I'm using one of these refined Weierstrass models that I have that I can engineer, then what I will find is that the analogous E-string theory actually has a broken flavor group. So the E8, in fact, is broken to an SU2 and E7 part, and the torsion actually takes care of the gauging of the diagonal Z2 center of the two. Of course, the other one I can engineer as SU1 times SO16 that I'm having here. But then I can also go to higher non-trivial theories that are of higher rank. Like I can take an E7 and I can intersect it with an SU2N flavor brane. If I go to the tensor branch, so when I'm removing the non-minimal singularity and by blowing up the base here, I get such a kind of quiver diagram here. So I will get a bunch of spheres with self-intersection -1 and -2, and I get gauge groups over them and a non-trivial meta content. For example, here I get hypermultiplets in the 56. Note that this theory I've constructed here, both E7 and SU2N have a Z2 center, but it is not gauged because I have constructed it in the generic Weierstrass model. But if I do the same in the Z2 Weierstrass model that has a Z2 torsion point, actually a part of this, or the diagonal flavor group of this, is actually gauged. And if I construct the tensor branch of this, we find that it's substantially different than the ungauged version that I'm having here. For example, I don't find fundamentals of E7 because that would not be okay with the center charge of the E7 Z2. But I also find that all gauge group factors that I'm having here are always compatible such that they have an Z2 center. So what I've showed you here are really two SCFTs that differ only by their global structure. They have the same flavor algebra structure, but here I have gauged a diagonal subgroup and I will get very, very different tensor branches and therefore SCFTs. And I can do it in a very nice geometric manner just by considering this torsion. Great. So this is some application. And now we want to see what is actually the bound on this torsion. And again, the argument is very easy motivated by physics. So this torsion implements this kind of quotient here, G mod Zn. And of course, not all groups have some center. E8 does not have any center. I cannot gauge it. And E7, for example, has just a Z2 center. But SUN has a Zn center. So you could just ask the question, if I'm able to engineer every SUN gauge group, shouldn't I be able to also gauge it by the center? I mean, this should be possible. From field theory, I don't see any arguments why this should not hold. And the anomalies are also not yet fine enough to really see or to really constrain such a modding. So what is actually possible? And like I just said, we know that, for example, elliptical Abioth threefolds are finite, so there must be a bound. But what is that bound? We don't know. And this is, of course, the thing we now would like to improve on, and which is something I did with Nadir at the end of 2019. So the idea is the following. And I hope I'm not getting too abstract here, but of course you can always ask questions. So what you actually want is you take an elliptic curve, you take your elliptic vibration that I've shown you here, and you want to fix an additional point of order P. Here, for example, I've fixed a point of order 2 and put it in the fundamental domain of the torus just at tau over 2. Okay, so obviously this is a point of order 2 because if I take this point, I add it to itself, I will get back at the 0 point. Excellent. So now, if I'm adding a D7 brane, yeah, and we have this shift that we just observed in the beginning by tau goes to tau plus 1, this torsion point is in general not going to be invariant under this shift. So such a D7 brane will not fix this torsion point. And if it is part of a compactification, I will not have a compactification that will preserve this model Weil group structure. Instead, if I put two D7 branes on top of each other, they will correspond to an SU2. This guy will actually leave this Z2 torsion point invariant because now it maps just onto this new point. So from this perspective, what you have to ask essentially is which kind of brane stacks or which kind of subgroup of your SL2Z modular group actually stabilizes your order P torsion point. This is the question you have to ask, because this is, if you know this subgroup, then you know which kind of branes you're going to have and which branes are compatible with your order P torsion point. This group is of course known, and it is known as a so-called congruent subgroup. So it's a subgroup of SL2Z where the entries are basically upper triangular or upper diagonal mod P. So these are the kinds of monodromies that are allowed that preserve an order P torsion point that you can use for gauging your center symmetry. But the actual question you would now like to ask, what is actually the moduli space of such an elliptic curve with an order P point? And this is of course also known in math. This is called as the so-called modular curve, or actually the compactified modular curve. And what this is, so this is here the modular curve for regular SL2Z. It is essentially those taus that live in the upper half plane, and then you mod out by SL2Z. But for the modular curve that we are now, then you get this keyhole structure like that you're having here, plus the point at infinity. So, and the structure that we are now after is that we don't mod only by full SL2Z by one of these congruent subgroups, because we only want to mod out those transformations that preserve this order P point. And what you're getting is some kind of this tessellated structure of this modular curve here. And I guess I should say that this modular curve itself also admits a non-trivial topology, and it is actually a topology of a Riemann surface. In the simplest example, it's just a P1 with a couple of cusps. Great. Speaking of cusps, the regular modular curve of SL2Z always has a cusp at infinity, but this tessellated version for preserving an order P point gets additional cusps. And these cusps can actually always be observed every time when multiple of these triangles here meet in one point. And the more triangles meet, the more width, so to speak, this cusp becomes. So the higher is, so to say, its vanishing order. And the nice thing is, this is exactly what is reflected in the model Weil torsion when you construct the explicit Weierstrass model that preserves this point. So this here is the Weierstrass model that preserves an order Z2 point. And the discriminant, and this is the important point, has precisely this additional I2 cusp. So the modular curve, which gives us the generic moduli space of an elliptic curve with a fixed order P point, is in one-to-one correspondence really with this Weierstrass model here and the factorization properties of the discriminant. And as you just see, if I put it now over a compact model, so these guys here are certain sections on the base, I will find this order 2 cusp here, and it tells you that I have an SU2 gauge algebra at the very least when I switch on this model. And this, of course, from physics terms makes sense. So if I force myself in a model where I want to have a gauged center symmetry of Z2, then the geometry tells you, yeah, well, then you better have at least something, some gauge algebra that has a compatible center at the very least. And this is in a very nice way encoded in the discriminant and in the Weierstrass model here. And in the modular curve, as I just said. Great. So this modular curve gives us actually a nice tool to consider the properties of a certain Weierstrass model with a fixed order p point without actually constructing it. That's super nice. So that's very nice. Good. So what happens now when I start to crank up order p points? What happens to this modular curve? And as I just said, if I do that, basically my fundamental domain of my modular curve gets more and more tessellated. For example, for Z2, I had this I2 cusp here, the lower left. If I go to Z3, I will get an order 3 cusp here. And my gauge algebra is going to be, or my gauge group is going to be SU3 mod Z3, because it's an I3 cusp. But if I go higher now, I find something surprising. I find that more cusps are actually there. I will always find gauge groups that are, or gauge algebra factors that are compatible with the center that is gauged. Like for Z5, it's an SU5. But what I will actually find is that the generic model will have more than one SU5 factor. You can actually find it here. There's one I5 cusp here, and then you have a bunch of additional cusps that are, well, maybe not so visible, but they are here at the lower left where more of these triangles meet. And if you increase it more and more, things are just getting worse. So for Z7, for example, you don't find just 2 SU7 factors, but you find 3. For Z9, you find SU9. You find 4 of these SU9 factors. And something that you can already see, for example, for K3, that when you want to have something which has torsion of degree higher than 8, then you will already overshoot the Euler number of a K3, because just the minimal gauge group is just too high. You will not be able to do it. And Z7 is just exactly at the boundary point of that. And something similar you can actually say for general elliptic Calabi-Yau n-folds, because you have so many gauge group factors now that they will actually start to collide, and your Calabi-Yau n-fold will admit a couple of non-minimal singularities that do not have a Krepin resolution anymore. And this is, in principle, the way how we were able to prove these bounds on model Weyl torsion for Calabi-Yau 3 and 4 folds. And in fact, they should actually hold also for Calabi-Yau 5 folds. So this is here the table that is known. A regular elliptic curve admits all kinds of torsion points, apart from Z11. And for example, a K3 has already a couple less. Like I told you, Z7, Z8 is allowed, Z9 is not, because of the argument I just gave. And DP9 itself is even more constrained. And what we're essentially finding is that Calabi-Yau 3 and 4 folds can only have that torsion that is also compatible with the DP9. And for the experts, the argument goes that all these gauge group factors that I have described, in fact, lead to 8, 12, 24 codimension 2 singularities, and those are known not to have a Krepin resolution. So if you introduce, if you want to have such a Weierstrass model, you actually get singularities that break the Calabi-Yau condition. And the nice observation from this is, of course, that the Calabi-Yau 3 and 4 folds have torsion, which is that of DP9, which precisely must be a finite abelian subgroup of E8. And this is going to be something which is important in a second. Okay, great. So we know a little bit about torsion, but about discrete symmetries. And of course, these discrete symmetries, I've told you in the beginning, are linked to these genus 1 fibrations that only have n sections. So I cannot play with all the nice knowledge that I have about elliptic fibrations, but I have to do something else geometrically, and way less is actually known about those guys. And as a motivation, these symmetries are actually really important for model building, because the MSSM that I was just showing you with its nice gauge group and so on and so forth is really cool, but it actually suffers from a lot of proton decay. So, so I can actually see it in the geometry that the proton decay allowing operators they're just there. You have them. All the models we have constructed suffer from a lot of proton decay, and a way to forbid it is actually enforcing an additional discrete gauge symmetry, for example, meta parity, to at least get rid of the most dangerous one of those. And you can do so, and we actually did. We did with Miriam, Ling, and Miang Lu like 2 years ago. We constructed such an F-theory model that has the MSSM gauge group and the exact meta parity that forbids the proton decay. But like I said, meta parity is just the first step. The best discrete symmetry that you want to have that forbids all proton decay is actually the one that has a Z6 proton hexality. And this is like the one you would actually like to engineer from phenomenological considerations, but we don't even know if it exists, because we don't know if Z6 exists as a discrete symmetry in F-theory. So I don't know how to construct this. So what you actually would like to have, you want to be able to construct higher discrete symmetries. And there's a couple of known constructions, and I was mostly involved in all of them, where you can go up to Z4. And actually something I should point out is that, that these discrete symmetries are, from a geometric point of view, highly complicated. And computing the spectrum of these geometries is highly non-trivial. And you actually need to invent new methods to do so, because even powerful computers are not able to compute them. And we actually did so a year ago by being able to compute the spectrum of these geometries via Gupa-Kumar-Baffa invariance and mirror symmetry. And well, this is also not trivial, but it is at least easier than being limited by computer power. So then I should also motivate that genus 1 fibrations have a couple of other highly interesting features that are interesting to explore. And I also did it a couple of years ago. Namely, they have the so-called multiple fiber phenomenon that you cannot have when your geometry has a section. So it's not possible in an elliptic model. And you have additional monodromies that lead to something like twisted affine fibers that I'm actually also working out right now with Lara Anderson and James Gray, and hope to publish soon. Great. But here is something I would like to show you, something very exciting that we found a couple of years ago, which is highly non-trivial. So a couple of years ago, we started to classify the generic gauge group you can have by describing your fiber in all kinds of different ambient spaces. So you want to describe your fiber in all 16 two-dimensional toric ambient spaces and see what the generic gauge group is. And the Weierstrass model, this is the polytope F10, is just one of those. And you can make such a table here where you give to each of these polytopes, you associate a generic gauge group, and they are of course all somehow connected by some geometric transitions that in the field theory will correspond to Higgs transitions. And there is a nice network that you're getting here. Yeah? And so you observe this, but of course, an elliptic curve is a Calabi-Yau, and the Calabi-Yau admits mirror symmetry, just as I said before. And actually, the ambient spaces that I'm having here, they are mirror dual to each other. Yeah, so F16 is a polar polytope to F1, and the two elliptic curves are dual to each other. So now what I observe when I look into the structure, and the mirror duality line is precisely here at the gauge group rank 3 case, I find that all the lower models that are genus 1 fibrations, they have a non-trivial discrete gauge symmetry, are exactly mirror dual to those models that have model-wide torsion in the upper layer. And I actually find that the free model-wide group part is fixed under this mirror duality transformation that I'm having, that I'm doing here. So this is actually exciting because it looks as discrete symmetries are in some way mirror dual to these quotient symmetries that I'm having here. Of course, the first question you're asking then is, okay, these are just 16 two-dimensional toric ambient spaces. Don't get too excited. This is maybe just a remnant of the simplicity of the model. So let's check this in a little bit more detail. Yeah. So let's describe our torus that is going to be the model for our elliptic fibration, not just as a single hypersurf in a 2D ambient space, but maybe you can be a little bit more complicated and describe it by 2 hypersurface in a 3-dimensional toric ambient spaces as a complete intersection. And there's of course a nice, and then you can, and of course these complete intersections are also subject to mirror symmetry due to Batirev and Borisov. Great. So you can do this for all 3,145 Neff partitions, so-called, that describe tori in 3-dimensional toric ambient spaces. And what you find is that the conjecture holds for all of them. Okay, so there seems to be something more non-trivial. And of course, this brings you forward to formulate a conjecture that discrete symmetries are mirror dual to these quotient symmetries. Okay, this is the conjecture you are having. And it's of course very nice because what we just did in the first part of the talk, we constrained model-wide torsion. So we know, and we have a strict bound on these dudes here. So we should also be able then to take this and have a bound on discrete symmetries. Okay, but of course this whole construction is, I actually don't even really know what it means, because what I'm doing is just literally mirror symmetry on the fiber. And what is there maybe something that I know that I can do in physics terms or what else? And in the end, it's just an elliptic curve. So how can I use this concept really, and how can I use this geometric intuition further? And where I will use this is actually that it will also naturally appear when I construct mirror symmetry for elliptic Calabi-Yaus. And this is going to be the last part that I'm considering. So in order to do this, I have to be a little bit more specific. And what I mean is I want to describe my Calabi-Yau as a hypersurface in a toric ambient space, which is given by some polytope delta. So I will never talk really about the Calabi-Yau hypersurface, but I will only talk about polytopes, or to be more specific, reflexive polytopes, delta, as they encode essentially all the data that's going to be necessary for the Calabi-Yau. So if I start and I have a reflexive polytope, and it has such a substructure here. So I have a substructure such that my polytope in general factorizes in such a form. So I have F, which is itself a 2-dimensional reflexive polytope, and B is some toric variety that identifies my base. And I have this structure here, this lower triangular structure. Then my Calabi-Yau hypersurface inside of that is going to be elliptically fibered or torus fibered, where the torus is described in this ambient space F. And then I have something which I call a twist T. Okay, this is essentially telling you how this fibration is twisted over the space B. Now, if I have a reflexive polytope, then there exists a polar polytope delta that I can just construct from that one. And the Calabi-Yau inside of that one is going to be the mirror dual Calabi-Yau x star. So now the observation, which is actually relatively easy to make, is that if T is, or the vertices of T, the twist, are part of this fiber polytope F, then the dual polytope will have a structure like that. So the structure is going to be that F is, or F star is, of course, the mirror dual itself of F. Then you will have kind of something like a polar structure of the base B, and also some kind of polarization of T, or like polar dual, I should say. But the important point is that it has exactly the same substructure that gives you a Calabi-Yau. And since F is a reflexive polytope itself, F star is also one, and therefore the mirror dual will also be torus fibered. And it's going to be torus fibered precisely in the mirror dual ambient space. And this is actually the way how I can include this duality observation that I had on the slide before into full mirror symmetry. So if this constraint here is satisfied, what I will observe is that mirror symmetry actually factorizes over fiber and base. So what can I do with this? Of course, what does it mean for my geometry? And what about that twist? What does it mean for the twist? And in order to tell you this story, I will go to a very, very simple example. And this is an example of K3. And I take this example because here I'm really able to draw the polytope and give you these nice pictures that I got from Sage. So,
can I ask a naive question, quick naive question?
Sure.
Here you are saying that mirror symmetry factorizes over elliptic fiber and the base of elliptic fibration. And suppose the Calabi-Yau is also K3 fiber. Does this also hold for the K3 fibration?
It holds for any kind of Calabi-Yau n-fold that is Calabi-Yau k-fold.
No, what I'm saying is that what I'm saying is that do you also have like a mirror of the K3 fiber and a mirror of the base?
Yes.
Okay, thanks.
It's a very general construction. You can even say you can be interested in a Calabi-Yau 4-fold that is Calabi-Yau 3-fold fibered, and it's the same over a P1. You can do the same thing. Okay. It's a very general argument.
Yeah. Thank you.
Sure. Thanks for the question. And I hope this one question was not the signal that people are getting too tired. But okay, let me continue. So this is an example for K3. So you start with the polytope delta, and it has the structures that we want. So here we have actually something which is called the minimal K3. It's just a Tate model, because the Tate model is the hypersurface in the polytope of 10. A Tate model inside inside our polytope. Here you have this two-dimensional subpolytope. Now you have to know that it's F10, but I can assure you it is. And you don't have any reducible fibers, so you just have this twist. It's some kind of trivial twist if you want. Now you construct the mirror of that, and what you find is, first of all, that the fiber itself lives in the dual ambient space of F10. F10, or the Tate model itself, is self-mirror, so the fiber type has not changed. So here nothing fancy is happening to the generic fiber, but you find that whereas on the left I didn't have any reducible fibers, I will have two E8 fibers that living on the two poles of the base P1. Oh, okay, good. That's interesting. Now what I'm doing on the left, I start to engineer an additional SU2 fiber by adding additional rays. And what I'm doing on the mirror side, I'm essentially peeling off vertices. And this is just clear if you have a little bit of a feeling for it, because this is, first of all, this is just a conifold, some type of conifold transition. But second, in order to get the SU2 fiber, I will have to do, I will have to tune certain monomials, and the monomials are precisely given by the points in the dual polytope. So here I'm putting an SU2 fiber, and I'm getting an E7 fiber. And it is actually, we observe that SU2 is the commutant in E8, and which gives you an E7. And actually you can go on like this. I can further put more and more fibers here, and I will find that I will more and more peel off of this E7 fiber, and I will always have a structure that is the commutant in E8. So this is, and I should of course also say, this is really something local that is happening here. I just operate on one pole in delta, or on one side on delta, but I don't do anything on for the other fiber. And here I still have the full E8 fiber. Excellent. So now I can start doing this with more non-trivial polytopes and non-trivial fiber types. For example, I can start with a genus 1 K3 that I'm having here. So here my generic fiber ambient space is that of F1. That one is not self-dual. And it's going to give me a genus 1 fibration with a Z3. And here, as you can see, I have an SU3 top put, well, literally on top. The mirror dual of that has a changed generic fiber type, and it's going to be exactly the fiber type that has Z3 torsion, just by the general picture I gave you before. And I have also non-trivial tops here. And what I find is precisely that the fibers that I'm having are precisely, again, commutants in E8. So here, the fiber I'm having here is just Z3, and I will get a full SU9, which I'm having here. And here I have, oh, I should have put SU3 here. And there on the right, I get an SU3 cubed mod Z3. So let's summarize the observations that we are making here. So in delta, we find two fibers that correspond to the groups G1 and G2. And in delta star, you have fibers that correspond to groups G1 star and G2 star. And they're both related by being the commutant in E8 of each other. Okay, this is actually an observation that already Berglund and Meyer in '98 made. But you can now ask the question, good, now that I'm having this observation here, how high can I go? If I want to get the discrete symmetry, I just have to feed some torsion group here, and how high can I go? And in fact, how high I can go is precisely labeled by finite abelian subgroups of E8. And those are in turn labeled by the Katz labels of the affine E8 Dynkin diagram. So if I'm now asking, what is the highest symmetry that I can get out of such a commutant here? It's given by the highest Dynkin label in the E6 Dynkin diagram. And note that this all makes pretty much sense, as we have just observed that the torsion groups are also precisely those that embed as the finite abelian subgroups of E8. And by this mirror duality rule, it is just clear that therefore the discrete symmetries are precisely of the same type. And this, of course, brings you to the conjecture that you would say that Z6 is the highest discrete symmetry you can engineer in F-theory on these genus 1 geometries, which is great news for Fino. So because we are actually barely able to construct this proton hexality. And it is in fact also consistent with the highest charged singlet that has been engineered geometrically recently by these fine gentlemen by using matrix factorization conditions. So they were able to construct a singlet with charge 6 under an abelian U1. And of course I can give it a VEF and I would get a Z6. But they were not able to get a Z7 to a singlet with charge 7 or so that I could Higgs to a Z7. So this is compatible. Very good. So this already brings me to my conclusion, which is a bit early, but I didn't get many questions, so I hope we have more time to chat. So what is my conclusion? So
okay, can I ask you another question?
Thank you, G. Yes.
This factorization of mirror symmetry conjecture can't actually be proved by the Strominger-Yau-Zaslow conjecture?
That's a very good, that's actually a fantastic question. I would love to show it, but I'm not able to do it. I mean, first of all, the SYZ is saying something about T3 fibrations, not T2 fibrations of your geometry.
Yeah, sure, but one can probably think of like, for instance, you applied 2 times T2 T duality in a fiber and then apply T duality in a base.
Yeah, that is something I could think of. Yeah, very good.
Okay.
Yeah, that would be interesting to explore indeed. Okay, good, fantastic question. So let me conclude then. So what we did was we tried to make progress in completing really the F-theory dictionary, and in principle say something about these abelian structures that you're having. And these abelian structures are important because they lead to U1 symmetries, discrete symmetries, and non-simply connect symmetries. And they are important, for example, in questions of the swampland, what is possible in string theory, but also really for very concrete model building, because these ingredients are, as also my speaker before just showed, they are just needed if I want to construct these more unified models in a string setting. But they are also interesting for SCFT questions, and there's a whole bunch on center symmetries, gauged center symmetries, that is actually center one form symmetries that this actually corresponds to, that I was not able to talk about. So what we did is we actually proved, and I hope I gave you like the rough idea of this proof, why these finite model wire groups are bounded. And they are bounded by being finite abelian subgroups of E8. And we did so by using the modular curve in order to get something like a universal model for these model wire torsion Weierstrass models. And this is, in fact, this is a hard math proof. So this is something we did. And then we were also able, and this is of course a little bit more conjectural, to put bounds on the discrete symmetries, or discrete gauge symmetries, by applying mirror symmetry and seeing that it actually is also bounded by E8. So this picture really fits relatively well together. So what is the outlook? What I want to do with this in the future? And of course, something that I would like to highlight again is that all this geometric progress that we are doing here is very, very flexible. I can use it for many, many things in physics. I can construct SCFTs, I can construct MSSM models, and I can know things about the swampland. So, so first of all, I would like to use this mirror symmetry dictionary to really explicitly, for example, via toric geometry, construct these Weierstrass models, or these genus 1 models with high n sections. And something I have also not been able to talk about is that in general, this mirror action on the base is highly non-trivial. And there's a lot of very interesting structures that you're having there. But then, of course, these genus 1 fibrations in general are very interesting in their own right. So first, of course, like I said, they lead to this multiple fiber phenomenon. And we have showed in a series of papers with Antonella Grassi and Laura Anderson, James Gray, that they actually lead to discrete symmetries that are coupled to superconformal field theories. Again, the discrete symmetry appears because you cannot have a section. And something else which is also very interesting is that these genus 1 fibrations have an enhanced set of monodromies, if you wish, that leads to something called twisted affine groups. And those guys lead to new physics that we are currently working on, and hopefully be able to publish very, very soon. And since the Tate classification of the resolution of singular fibers is exclusively coupled to the Tate model, it does not apply to G-1 fibrations. And actually, for each fiber type, you, in theory, would now have to you would have to perform a similar classification of the resolution of singular fibers due to these additional monogemies that you are having. And this would, of course, be a nice research program that would be very interesting to trigger with the people from the Yao Center. And finally, I should say that this whole structure, this factorization of mirror symmetry into a fiber and a base part, has a very strong link that we are currently exploring to so-called Doran-Thompson-Harder mirror duality that was put forward just a couple of years ago. Good, but with this, I would like to conclude, and yeah, I hope it was interesting. Thank you.
Yeah, thank you very much. If anyone has questions, please unmute yourself.
Also, in case if something was a little bit unclear, I would be very happy to elaborate on some things. I mean, I think we touched on a lot of topics, and it's very hard to give, at least from a mathematical point of view, to give it justice enough.
If I may, probably I would like to ask another question.
Yeah, go ahead.
What is this Doran-Thompson-Harder mirror duality?
Very good. So these people essentially made a similar proposal already, where they are actually saying, if I have a Calabi-Yau n-fold that is a Calabi-Yau n-fold that has a Calabi-Yau k-fold subfibration structure, I can perform mirror symmetry, and I will get something similar. I will get a new Calabi-Yau that is fibered by the mirror dual Calabi-Yau k-fold, essentially. But the way how they proposed it was that they actually said that how can I say? So first of all, I think the base was always a P1. So the action on the base is relatively simple, whereas we we are, so to speak, doing this the opposite thing. We take the simplest Calabi-Yau fiber, but leave the base very general, and they have a general Calabi-Yau k-fold fiber and left the base very simple. And okay. That is one of the things. I mean, the story is relatively long, but one other proposal of the way how they actually looked at this was by essentially trying to perform mirror symmetry on log Calabi-Yau. So they essentially try to, for example, to degenerate a K3 into its DP9, into two DP9 pieces, and try to perform mirror duality on these non-Calabi-Yau pieces, and then glue it back together, the mirror dual, and see what they got. And this is essentially how they find these similar observations. Yeah.
Okay, thank you.
Mm-hmm.
I have a naive question. I'm not familiar with this geometry, but geometrically, it looks like you can orbifold for any Zn, but now you're saying that there's some upper bound on n, and what happens if I try to create a very large n orbifold?
Yeah, that's very good. So actually, this is yeah, you can orbifold. That's true. But if I, for example, try to orbifold a torus, you're already getting in trouble, because a torus, I mean, let's say the torus is like my analogy for the easiest Calabi-Yau that I'm having. But the torus orbifolds, they are of course exactly also bounded to not exceed Z6, because you have to have a certain symmetry of the underlying lattice. So there you will, for a compact example, you will have a natural constraint by this. but is the question really, what if I try to orbifold these geometries, or is that what you're asking?
You are saying that if it's torus, you cannot really make an orbifold for large n.
Right. And I mean, you can take a Z2, Z3, Z4, and Z6. Period. That's it.
Yeah. Okay.
You cannot go higher. Yeah.
I see.
So this is just bounded really by the possible well. I mean, you have to, in order to take an orbifold, you have to have a certain symmetry, and you can, for torus, you cannot choose anything, essentially. Yeah.
Okay.
But I mean, of course, constructions that you can do, and this is, like I said, something we have worked on, and this is just to elaborate maybe a little bit on this, something where these multiple fibers come about. Something you can do, which is a very interesting construction, is you can take a quotient out of an elliptically fibered Calabi-Yau threefold, for example, and you can take a quotient that acts free and preserves the fibration. So I have a geometry, I can quotient it out, and again, not any kind of quotient as possible. I should say that a constraint really comes also here from the compactness of the geometry. That is usually the things that starts to bound, that starts to put bounds. But if I do such a quotient construction, I will actually, one can see that they can never act, they will always act freely on the zero section. So a zero section will never be preserved by such a quotient, for example. And this, in fact, is something where you can construct these multiple fibers in a very nice way. And there's yet again a deeper connection to torsion groups and genus 1 fibrations. Yeah. And yeah, there is this indeed, and this is actually something we have unfortunately not have explored so much. So these discrete symmetries and how you couple them to SCFTs is something that is very natural to do. I mean, and if you want, we have used these model-Weyl structure a little bit to couple them to SCFTs and to get these non-simply connected gauge groups. But coupling discrete symmetries to SCFTs from a geometric point of view is a straightforward thing that one should do next. Yeah. This indeed.
Okay. Any other questions? If not,
I have a small question.
Yeah, please.
So I think the introduction, you mentioned that we can get n equal 1 supersymmetric field series in 12 minus maybe 2n dimensions. When we take a Calabi-Yau n-fold, right? But what about the case of Calabi-Yau 5? In this case, we can get just 1 supercharge rather than 2. I guess, yeah, we get 2 supercharges.
Oh, that's a good question. No, you're right. I think it's a 2,0 theory. Yeah, you're right.
So that is exceptional case, right?
Yeah, that's good. It's yeah, it's an exceptional case. You're right. You're right. Good question. Indeed. Yeah, 2 dimensions.
But is there any known models for like 2-dimensional 0-2 series emerging from Calabi-Yau 5 in F series?
That's a very good question. Indeed. Yes, this is a program that has been put forward by Sakura Shefanameki, Timo Weigand, and Jonathan Heckman, and various other people. And sorry for possibly missing a couple, but this is precisely what they were doing, and it's a very nice thing to do. So yeah, precisely. You take an elliptic Calabi-Yau 5-fold. And I mean, just as I could have taken type 2b on a Calabi-Yau 4-fold, I guess, or heterotic string on a 4-fold. And you get these 2,0 theories, and you get some Gaussian sigma model. And so yeah, they were doing it, and you can do it. It's of course having its own set of problems, but it's very interesting, and you can do it easily in a toric fashion. And the nice thing that you can really do there, if you write down your theory and you do the F theory reduction and you consider the theory that you're getting in 2 dimensions, and you count all your degrees of freedom right, what you find is that your 2-dimensional supergravity anomaly, so to speak, is cancelled. But it's very, very, very subtle. You really have to take into account all the degrees of freedom, and it's a very satisfying program if you do it. So yeah, you can do it, and it's a program that people are doing, indeed. So actually,
yeah,
I was
I'm wondering whether, yeah. So is there any reason to get that chiral supersymmetry in this case? What about the 1,1?
Good question. I believe not so much is known about this construction. I know the 2,0 has been done, and I think even the 2,2 is hard to. At least not that I know of that people have done it, but it's also not terribly explored. I mean, I think there are like 3 or 4 papers on this that lay the ground essentially for these constructions, but I think there's not too much that people have played around with. So it's an interesting question, yeah, for sure. Yeah.
Thank you.
Sure.
Okay, if there's no more questions, let's thank the speaker again. And I stop the recording.